Speeding at sea, it's me, Z. A lot of you online wanted to hear about how space and time can swap into black holes, so let's just jump straight into it. This video is split into a few parts that I've timestamped below, which will take us through a rigorous exploration of causality and what exactly being able to swap space and time means. Let's first start with a simple example on Earth. Let's say that there's a remote control activating a television a certain distance away. In this case, about 1.5 meters. A useful hint is that 0.3 meters or 1 foot is about 1 light nanosecond. So the TV would be about 5 light nanoseconds away. From ADA, an observer in the inertial reference frame of the remote control on the TV, clicking the remote control would activate the television. But let's say that there is an outside observer, Bob, who's traveling at 2/5 the speed of light. In this inertial frame, does the turning on of the TV cause the remote control to be activated? We know that this would not be possible because it violates the second law of thermodynamics. It would decrease the entropy of the system. So how is it that with time dilation and length contraction are present when traveling at relativistic speeds, the causality of an event still remains the same? We'll need to define the space-time interval in space and time, as its name suggests. This is defined similarly to the Pythagoras theorem, and it's almost sort of as like a distance in space-time. The space-time interval squared is equal to the difference in time squared minus the difference in position squared. Now let's draw a quick diagram for our scenario. The remote control is constant in position as time progresses, so we can draw it as a line at position 0 shown here, which means that it doesn't move. Similarly, the TV is also constant in position over time, so we can place it over here about 5 light nanoseconds away. The signal from the remote travels at the speed of light c. In that case, the position traveled in light nanoseconds is equal to the time that is progressed in light nanoseconds. So we can draw that as a dashed line here. But what does Bob, our relativistic traveler, see? Here. The position must be orthogonal with respect to our speed limit c, so we can draw those axes there. These primed axes represent Bob's inertial reference frame. The remote control's position is at point P here, but what happens as the signal arrives to the TV? In ADA's inertial frame, it will simply travel at speed c to the TV's constant position. But in Bob's inertial frame, the signal still travels at c, but now we need to transform it to his reference frame back onto the time axis. We can do this by moving parallel to Bob's position axis to get the time of arrival at the TV. Again, looking at Bob's reference frame in time, the TV turns on after the remote control signal arrives. Causality still holds. But when does this not work? Let's take a look at what happens when the signal is traveling faster than the speed of light, say at v equals 3c. This time, Q, when the TV turns on, will not be along that dashed v is equal to the speed of light line. Instead, we can draw a new dashed line for the signal's trip, which moves 3 light nanoseconds in position over 1 light nanosecond in time, since the velocity is 3c. In ADA's reference frame, the TV turns on after the remote control signal arrives. Causality still holds. What about Bob's reference frame? To find out when the TV turns on with respect to Bob's frame, we again move parallel to Bob's position axis to get the time of arrival at the TV. And if you look at Bob's time axis, something has changed. Now the TV turns on before the remote control signal is activated. That's why no signal can go faster than the speed of light, because causality and the second law of thermodynamics must hold. When we are under that speed limit, space-time intervals between these events are invariant for all observers. Different events have different space-time intervals, and they can be described by time-like, space-like, and light-like separated. The first example with the TV was light-like separated. The signal was moving at the speed of light, and the distance traveled is equal to the distance light travels in time. Our second example was space-like separated. In this case, the signal was superliminal, faster than the speed of light. Within this category are also events that occur at the same time. Finally, if we had a signal moving slower than the speed of light, then the events would be time-like separated. All inertial observers will agree if a space-time interval is time-like, light-like, or space-like. And as we found, only light-like and time-like events can be causally connected due to the speed limit of light. Okay, so let's go back to black holes. As you may know, they are gravitational behemoths where even light can't escape past its event horizon. And that's the same for everything even outside light. Inside a black hole, you can't define a distance because space itself is falling into the black hole. You can't define a time because your time axis, described by the speed of light, is also falling into the black hole. However, it's not that space and time are swapping. It's rather the labels that we typically correlate as space and time in the graphs, before or in previous examples, are no longer attached. Going back to our space-time intervals above, the space-like and time-like coordinates that we described will not swap and will remain preserved. For instance, that's why we use Kruskal coordinates instead when describing black holes, which preserves this invariance. The main difference with this coordinate system is that the x-coordinate lines are now hyperbolas and the time coordinate lines are now straight lines. This represents the infalling light rays and outgoing light rays bent from the gravitational field. If you explore the parameter space, there are actually some really interesting results, such as a default black hole where nothing can escape, or a region, a white hole, where nothing can remain, a parallel universe that is completely isolated from the other, or even a bridge between two universes. That is, if you could go faster than light. In this coordinate system, inside a black hole, time remains time, and space remains space. So far, we've been looking at causality as a property of time. One thing happens after another. Now, all future directions point radially inwards, similar to how we all move towards the future in our everyday lives. The main takeaway is that causality is now jumbled up in space and time in a black hole, and we need to be cautious about how we interpret space-time coordinates in these extremes. Thanks so much for listening and for all the enthusiasm online. I'm so excited to make more explainer videos like these. Comment down below if you have any ideas, and don't forget to follow me on X, formerly known as Twitter, or on YouTube for more physics, astro-aerospace news, surreal memes, or nerd content from your favorite physics VTuber. Signing out.